So then let's move on to the next speaker, who is Zhang, who is going to talk about high-throughput de novo proteome identification.
Hello everyone. Today I'm going to present our really newly coming out results, not yet published. It's about high-throughput de novo proteome identification aided by Translatome sequencing. When we get a lot of mass spec spectra, we have two basic strategies to deal with them. One is database search. So we have a database, so we compare these spectra with the database and determine which one is that. And another strategy is de novo sequencing. So we don't use a database, we directly figure out which peptide amino acid sequence from the spectra. Currently, most of the people use database search, and the de novo sequencing were not applicable for high-throughput identification. Why is that? Because there's one thing: false discovery rate. Since de novo sequencing don't have a reference database, there's no way to assess accuracy for that. So we have two major questions. First, how accurate or how inaccurate is the de novo identification? And the second one is how to control the FDR for high-throughput de novo identification. To assess this, we have to use some mass spec data. So we use the mass spec data for 3 hepatocellular carcinoma cell lines in CHBP approach in 2013. And we used the de novo algorithm of P novo plus. So after the de novo sequencing, this P novo plus resolved 80 to 90% of the mass spectra, which is pretty high. Then we have to use a standard to control, or as a reference, to control the accuracy for de novo sequencing. And what we are going to use is Translatome sequencing, or RNCC. And that is, which means that we sequence the translating mRNAs. Because in steady state cells, translating mRNA to protein, there's one-to-one correspondence. Why not we use transcriptome directly, which is much more easier to do? Because 5 to 25% of the mRNA are not translated. So if you use transcriptome as a reference, you will introduce 5 to 25% of the false positives. And so this strategy, so the RNC mRNA analysis has been adopted as the fourth resource pillar in CHBP. When we used RNC-seq data to control the quality of the de novo identification, we figured out that only a small fraction, so namely approximately 20% of the de novo peptides were supported by translation evidence, which means that the de novo results are highly error-prone. Therefore, the quality control by external reference, especially the RNC-seq, is very necessary. Where do the errors come from? We all experience a lot of noise in the mass spec data. So if we don't use any reference, the de novo algorithm is very sensitive to such noise, resulting in partial errors. So we see that in these parts, the peaks are very clear and crisp, so we can very nicely define the amino acid sequence. But in this region, due to the noise, the algorithm made of wrong detection. So the solution, our solution is to use the peptide sequence tag, or PSTs, to identify the peptide. Because we can identify a peptide using its unique subsequence. So this strategy was established firstly by Matthias Mann in 1994. Using the RNC-seq data as a reference, we can calculate we can estimate the FDR for PST. So if the PST length is long enough, more than 9 amino acid long, we can control the FDR under 1%. And this length is equivalent to the up-to-date guideline of HUPO. And on a peptide or protein level, RNC-seq can directly control the quality. So how powerful is such a PST-based proteome de novo identification? From these three cell lines, we identify 12,000 to 13,000 proteins in single experiment, not multiple experiment, so single experiment. The RNC-seq identifies approximately 14,000 translating mRNA species. So you can see that the protein identification power is approaching the RNC-seq. If we seek the proteoforms, we can identify almost 18,000. Compared with traditional database search, we see that de novo methods largely exceeds the multi-engine database search. And just from these three cell lines, we identified 814 missing proteins, by which most of them we identified more than 2 unique peptides. And we used MRM to verify de novo only peptides, and most of them can be verified, including the missing proteins. Using such strategy, we can directly identify the single amino acid polymorphism like this. So we see this is in the database sequence, and we see here is SAP. And it is also possible to detect fusion proteins directly. So this is a peptide resolved by the de novo method, and actually one half is from this gene, and another half is from this gene. So they are from the different genes. So probably this peptide comes from the fusion protein. So a summary: the de novo peptide sequencing itself is not accurate. Using the RNC-seq, we can apply de novo peptide sequencing on high-throughput proteome identification. And this strategy is very efficient, approaching the sensitivity of RNC-seq, and also this kind of high-throughput de novo proteome identification can potentially detect SAP and fusion protein directly. Okay, so I will stop here. I thank my students and the collaborators, Dr. Gong and Dr. Hao Qi, for their assistance, and thank you for your attention.
Thank you for a very fascinating talk. We have time for questions. You have kept very good time.
So 840 is a huge increment of missing P234 proteins.
Oh, yes.
Is this published, or is the data set available? Will it be available to be incorporated into the next version of Peptide Atlas and next one?
We just got these results last week, so it's not yet published. but yeah, later we will include it.
I just wonder for false positive rate. So you validate with the MIM technology.
Yes.
But I just wonder what percentage you did validation for all of the identification. How much percentage you did validation by this method?
So we randomly took 82 peptides for identification, and we successfully verified 61.
But I think you still have 21, so
yeah.
It should be, if you want to publish, maybe some guy will worry about it. So maybe you need more validation, maybe also other method to see your identification is correct.
Yeah, it's a very nice comment, and we will do that.
Last question.
In the fusion peptide that you show, the few amino acids that are coming in between.
Yeah.
Where are they coming from? The DDA that you are showing, because I am seeing here that KITDAE is there, and then the few amino acid DDA is not here.
It's not here. Yeah. There are 4 amino acids in between missing here. We're also wondering why it's like that, and probably some wrong identification for a few amino acids by the de novo algorithm, and we are going to do the PCR to verify whether this is really a fusion, the fusion peptides, or just an overlap of 2 spectra.
But if you take out those 3 amino acids, then the entire assignment will again go haywire. It will not be this many number of matches that mass will not match. That's it.
Yeah.
Okay, thank you very much. And we will come to the last presentation in the session, which will be on JPOS by Shujiro